Hello, my curious friend, and welcome to Deep Field Channel. Tonight we're stepping into a territory you inhabit completely, every single minute of every single day, without ever having been handed a map. A chemical territory, precise down to the smallest detail, sitting just a few centimeters behind your eyes right now as you rest, quietly governing what you crave, what you chase, what you let go of, what becomes habit without ever having been a decision. I promise to try not to make this topic so vivid that it steals your sleep, but it will be difficult. Before we begin, I would love to hear in the comments or in the world you're listening from tonight. And if tiredness gets the better of you, just leave a simple hello. It may seem small, but that tiny gesture tells YouTube that our space is a welcoming one and helps us bring more tired minds here to unwind with us. If you enjoy our scientific journeys, please leave a like and subscribe. And to those of you who are already part of our community, thank you so very much. If you would like to get even closer, consider becoming a channel member. Members receive early access to videos before anyone else. The link is in the description. Now, wherever you are, find a truly comfortable position. Let your shoulders sink down, release your jaw. If sleep arrives during this journey, accept the invitation graciously. Let us begin. There is something inside you that acts before thought arrives. Not alongside it, not right after. Before. You're lying down, the light already off, with no apparent urgency, and then your hand reaches for your phone without a single intention having been formed. You open the refrigerator without being hungry. You click on one more episode when you had already decided to sleep about 10 minutes ago. This force that precedes choice has a name. It has a precise address inside the human skull. It has a scientific story that takes a long time to tell, because what it reveals about us is somewhat unsettling. It is called dopamine, and for decades it was celebrated with a label that seems right at first glance, but that, the more closely you examine it, the more it reveals itself to be imprecise in a way that changes everything. Dopamine entered popular vocabulary as the pleasure molecule, the happiness hormone, the substance behind every good feeling life can offer. That story is, at best, incomplete. Because dopamine is not pleasure. It is something that comes before pleasure. Something more primal, more fundamental, and in many ways far more powerful than any fleeting sensation of satisfaction. Dopamine is anticipation, the premonition that something good is near, the pleasant tension of maybe. It lives in the distance between desire and fulfillment, in that space of possibility that precedes any arrival. It is in this territory, in the zone of what has not yet happened but could happen, that the system reaches its peak of activation. Think about the difference between the smell of coffee being brewed in the kitchen and the first sip from the cup, between the buzz of your phone before you see who sent the message and the moment the message finally reveals itself, between the day you buy a plane ticket and the instant the plane lifts off the ground. In each of these pairs, the element that comes first generates more activation in the dopamine circuits than the second one. This is not metaphor or poetic interpretation. This is what experiments show when they measure neuronal activity with millimeter precision in real time. And the result firmly contradicts everything common sense had assumed for so long about what exactly makes us feel good. The first great misunderstanding about dopamine is confusing it with the pleasure we feel when something good happens. The second, equally widespread, is believing that wanting something and liking something are the same experience, two inevitable sides of the same coin. Neuroscience spent decades mapping these two systems and found something that seems profoundly counterintuitive, but that withstands every attempt at simplification. Wanting and liking are distinct processes, supported by different circuits, fueled by different substances, capable of operating completely independently of each other. Liking, the experience of pleasure in the exact moment it occurs, primarily involves the brain's internal opioid systems, substances that the body itself produces and that create that sense of wholeness and satisfaction accompanying certain experiences. Wanting, The drive to seek something that is not yet here is dopamine's territory. The consequence of this separation is both disturbing and illuminating for anyone willing to look honestly at their own behavior. It is entirely possible to want something with intensity and persistence without feeling any real pleasure when you finally obtain it, and it is equally possible to feel genuine pleasure in something without having desired it with any particular anticipation. Who has never found themselves pursuing something with considerable energy, only to discover, at the moment of obtaining it, a diffuse disappointment, a hollow lightness where fullness was expected, a feeling of where is what I wanted so badly. This experience is not a weakness of character or existential ingratitude. It is dopamine revealing its most honest nature. It is the engine, not the destination. Chemically, dopamine belongs to a family called catecholamines, the same family that includes adrenaline and noradrenaline, substances everyone has encountered in the context of emergency reactions and states of intense alertness. This kinship is not accidental. All catecholamines share the function of mobilizing the organism, preparing the body and mind for action, creating the internal conditions necessary for movement towards something or away from something. Dopamine, however, works predominantly within the brain, while the other catecholamines also exert their effects in the peripheral body, in the racing heart, the constricting blood vessels, the expanding lungs in the face of danger or excitement. It is produced from an amino acid called tyrosine, which the body extracts from everyday foods that most people consume without thinking about it. Eggs, legumes, lean meats, aged cheeses, nuts. Inside specialized neurons, tyrosine undergoes successive enzymatic transformations, first converting into an intermediate substance called levodopa, and then, finally, into dopamine. From there, it can be used immediately as a chemical messenger between neurons, stored until the right moment, or converted into other members of the catecholamine family, depending on what the organism needs in that specific context. What distinguishes dopamine is not its chemical composition, which is relatively simple by the standards of brain biochemistry. It is where it exists within the brain, which routes it travels, and what it does when it reaches its destination. The neurons that manufacture dopamine are surprisingly few for something so powerful. They're concentrated mainly in two small regions deep in the midbrain, the most evolutionarily ancient part of the brain in evolutionary terms, the part we share with reptiles and with the earliest mammals that appear in the fossil record. One of these regions is called the ventral tegmental area, a modest cluster of cells located almost at the geometric center of the brain, a structure so small it could fit inside a grain of rice, and yet it projects its influence all the way to the most distant cortex, the most recent, the most distinctly human. The other producing region is the substantia nigra, named for the dark pigment its neurons accumulate over a lifetime, like leaves darkening with time, and when they are gone, they leave a visible clearing behind. From these two modest origins, projections extend to territories far removed within the brain. The prefrontal cortex, right behind the forehead, responsible for long-term planning and the ability to resist immediate impulses in the name of future goals. The nucleus accumbens, central to processing motivation and forming what we might call behavioral appetite. The striatum, involved in both learning motor sequences and responding to situations of reward and punishment. Each of these connections serves distinct purposes. When any of these circuits is significantly disrupted, the result is a specific and predictable set of difficulties. From slowness of movement to loss of initiative, from difficulty maintaining focus to profound alterations in the perception of oneself and of the future. The magnitude of this system becomes evident in an almost paradoxical way when you consider what happens in the progressive absence of dopamine in the most basic motor circuits. In certain clinical conditions, the neurons producing this molecule in one of the regions we mentioned begin to die progressively, silently, over years that accumulate without warning. The system has a remarkable ability to disguise partial losses. Surviving neurons increase their output, circuits reorganize to work with what remains, and the organism continues functioning within a range that does not betray what is happening inside. It is a form of biological silence that only reveals itself when the warning has already arrived too late. A reminder that dopamine is not merely emotional, not merely motivational. It is in the most everyday gesture, in the step taken, in the cup lifted without thinking, in the smile that begins before it is complete. But there is something even more revealing about the behavior of this molecule, something that experiments uncovered and that deserves to be presented here as the first great counterintuitive fact of tonight. When researchers measured with ultrafine electrodes the activity of dopaminergic neurons in primates during carefully controlled reward experiments, they found a result that overturned decades of assumptions. The peak activation of these neurons did not coincide with the moment the animal received the expected food. It happened before, at the instant the visual signal appeared announcing that the reward was on its way, and when the promised reward did not arrive after the signal. When the expectation that had been created went unfulfilled, dopaminergic activity did not simply return to normal. It plunged below the baseline as if the system were expressing in chemical language the specific texture of disappointment. The system does not celebrate what has arrived. It stirs at what might arrive. This mechanism has evolutionary roots of great depth. In a primitive environment where food, shelter, and safety were neither guaranteed nor rarely predictable, it made no adaptive sense whatsoever for the brain to merely react to what was already present. What was needed was a system that would move the organism before the reward appeared, that would keep the animal moving toward what had not yet been obtained, that would create the impulse to seek even in the face of uncertainty about finding. Dopamine is that system. It is the engine of the search, not the flavor of arrival, and that is precisely why it navigates so effectively through our contemporary world, a world built, often deliberately and with precise understanding of this mechanism, to exploit this evolutionary principle with a precision that no natural environment ever achieved. The phone that buzzes without immediately revealing what has arrived. The loading bar that is almost complete but has not yet finished. The next episode that starts automatically 3 seconds after the previous one ends, without you needing to make any decision. All of these elements capture dopamine in a state of prolonged and renewed anticipation, because it is there, in that undefined zone of maybe, that the system reaches its peak activation and refuses to rest. Where then does the energy come from that sustains these circuits throughout an entire lifetime? What are the laws that determine when the system fires with force and when it remains at rest? What feeds the original source of all this searching that never seems completely satisfied? This question will hang here, like a seed planted at the edge of sleep, waiting to find soil quiet enough to bloom. The answer to the question left hanging requires that we enter the interior of the brain itself with more attention than we usually have available during the day, because dopamine is not a free substance floating randomly among nerve cells like mist in a corridor. It travels along specific routes, each with its precise function, each with its own vocabulary, each responding to different stimuli with firing patterns that neuroscientists took decades to map with the sophistication we now possess. And to understand how a single molecule can accomplish things so radically different, from controlling the fluidity of movement to fueling creativity, from sustaining emotional bonds over years to triggering compulsive behaviors that resist any rational argument, one must know these roots and understand why they exist separately. The human brain has 4 main dopaminergic pathways, 4 distinct roads that depart from the same modest origins we mentioned, and arrive at destinations so different that it is hard to believe they are being fueled by the same molecule. This separation is neither accidental nor a whim of evolution. It reflects the fact that dopamine serves functions so diverse that mixing them into a single indiscriminate circuit would produce functional chaos. Specialization is the solution evolution found to use the same chemical messenger in multiple contexts without one interfering with the other. The first of these pathways, and the one that became best known because of its role in motivated behavior, is called the mesolimbic pathway. It runs from the ventral tegmental area to the nucleus accumbens, passing through other structures of the limbic system, that network of deep brain regions intimately linked to emotions, affective memory, and the processing of personal meaning and experiences. It is the mesolimbic pathway that fires when you taste something delicious for the first time, when you hear music that moves you in a way you cannot fully describe with words, when you receive a message from someone whose voice you would love to hear. But more than simply celebrating what is good in the moment it is good, this pathway learns what is good. It records patterns with a fidelity that conscious memory cannot match. It associates contexts with rewards in ways so subtle that you do not even notice the learning happening. That is why the aroma of a place you visited during happy times can generate an internal response of lightness and anticipation before you have even crossed the threshold. The mesolimbic pathway is always cataloguing, always creating internal maps of where pleasure was found before, always pulling behavior back toward those territories it has marked as rewarding. The second pathway is called the mesocortical pathway. It originates at the same point as the previous one in the ventral tegmental area, but its destination is completely different. The prefrontal cortex, the most evolutionarily recent region of the human brain, the one that allows us to plan long sequences of action, reason about hypothetical situations, consider the future consequences of present decisions, and resist with some degree of consistency immediate impulses that, if followed, would compromise longer-term goals. When you're focused on a difficult problem requiring multiple steps of reasoning, when you weigh two options and carefully consider the implications of each one beyond the immediate horizon, when you have chosen to delay an immediate reward in favor of a goal that takes months to materialize, the mesocortical pathway is providing the dopaminergic fuel for that cognitive effort. Deficits in this pathway are associated not with a lack of intelligence, but with difficulty sustaining attention on a task over time, with weakened working memory, with a tendency to let the environment dictate behavior rather than allowing goals to guide it. The third pathway is the nigrostriatal pathway, connecting the substantia nigra to the striatum, travelling a route that for a long time was associated almost exclusively with motor control. It is what allows voluntary movement with smoothness and precision. Every step taken with the naturalness of someone who does not even think about what they are doing. Every gesture learned and progressively automated through repeated practice. Every motor sequence executed with the elegance of someone so immersed in the action that the distinction between intention and execution disappears. All of it rests on the silent and constant work of this pathway. When it begins to fail for reasons we will explore later, movements become rigid, slow, initiated with a difficulty that those on the outside cannot fully imagine. The elegance of everyday gesture reveals in this contrast just how much it was the product of an extraordinarily precise system operating in the background. The fourth pathway, the tuberoinner-fundibular pathway, follows a shorter route than the others, connecting the hypothalamus to the pituitary gland and regulates the release of certain hormones, including prolactin. It serves as a reminder that dopamine is not only a molecule of the thinking or emotional brain, it touches the endocrine system, reproductive functions, metabolism, body weight regulation. Dopamine is part of an integrated organism in ways that go far beyond what popular narratives about motivation and reward usually acknowledge. How does the transmission mechanism itself work? How does a molecule so small manage to produce effects so large across territories so diverse? To understand this precisely, imagine two neighbouring neurons. They do not touch each other directly. Between them exists a microscopic space called the synapse, a gap a few nanometers wide separating the transmitting neuron from the receiving neuron. When the first neuron needs to send a message, it packages dopamine into tiny vesicles and releases them into this space. The dopamine molecules cross the synaptic gap by diffusion and fit into specialized receptors on the membrane of the next neuron, proteins with shapes precisely molded for this specific molecule, like a key that opens only that lock and no other. When the fit occurs, the receiving neuron changes its internal state according to the type of receptor that was activated. It may fire a new electrical impulse, it may suppress a response that was about to happen, or it may trigger a cascade of chemical reactions inside the cell that alter how it will respond to future stimuli. This contact is not permanent, nor should it be. After delivering the message, dopamine is reabsorbed by the neuron that released it through specific transporter proteins, or it is broken down in the synaptic space itself by enzymes that dismantle it into inactive substances. The system is calibrated with temporal precision to last exactly as long as necessary to transmit the information. When this balance is disrupted by substances that block the reuptake transporters or that force massive dopamine release independent of the natural signal, the result is an intensification and prolongation of the signal, far beyond the limits for which the system was designed over millions of years. The story of how we came to understand this system is one of the most human chapters in 20th century science. In 1957, a Swedish pharmacologist named Arvid Carlsson was working with laboratory animals exhibiting symptoms similar to those of Parkinson's disease, experimentally induced. His colleagues already knew that a compound called levodopa could reverse these symptoms dramatically. But no one had understood why, and most researchers at the time believed dopamine was merely a transient chemical precursor on the way to synthesizing other substances with no significant function of its own in the nervous system. Carlsson suspected this perspective was wrong, and using a visualization technique called histofluorescence, which made neurons containing certain substances glow under ultraviolet light, he was able for the first time to map exactly where dopamine was located within the brains of animals. What he found was unexpected by the standards of what was assumed at the time. Dopamine was not distributed evenly throughout nervous tissue. It was concentrated in highly specific circuits, in precise pathways linking deep regions to more distant ones, with an organization that suggested functional purpose rather than mere casual distribution of a chemical intermediate. And when these circuits were experimentally damaged, the animals lost the ability to initiate voluntary movements in a coordinated way. When they received the precursor substance that the brain converted into dopamine, they regained that ability in a way that seemed almost miraculous to those witnessing the experiments for the first time. The conclusion was of a clarity that startled the field. Dopamine was not a minor messenger, it was essential. It was the difference between movement and stillness, between initiative and paralysis, between life organizing itself into action and life remaining trapped within itself. In the year 2000, decades after presenting his findings in a field that was slow to accept them, Arvid Carlsson received the Nobel Prize in Physiology or Medicine for this work. In the years following the original discoveries, the consequences for clinical medicine were immediate, especially for patients with Parkinson's, for whom dopamine replacement through levodopa represented for the first time in history the concrete possibility of regaining movements that had been lost in what seemed like an irreversible way. The most elegant discovery about dopamine would come in the following decades, when researchers with increasingly sophisticated equipment began measuring in real time the individual activity of dopaminergic neurons, while animals performed carefully controlled reward tasks. What they found became known as reward prediction error, and it is one of the most influential concepts modern neuroscience has produced, a concept that, once you understand its mechanics, retroactively reorganizes decades of behavioral observations that had resisted explanation. The mechanism works like this. When an animal receives a reward completely unexpectedly, without any prior warning, without any signal it has learned to associate with the arrival of something good, the dopaminergic neurons fire intensely at the exact moment the reward arrives. The brain is learning, this happened unexpectedly, it was good, I need to record this context so that next time I can anticipate it. But when a repeated pattern is established, when a specific signal consistently precedes the reward over many repetitions, something fascinating and counterintuitive happens in the firing pattern of the neurons. They stop firing intensely when the reward finally arrives. They begin firing when the signal appears. Anticipation functionally takes the place that reward once held in the firing circuit. And when the signal appears but the promised reward does not come, When the created expectation goes unfulfilled, the neurons drop below their normal firing rate. The system registers the discrepancy between what was predicted and what happened. It learns through negation with the same effectiveness with which it learns through affirmation. It is this learning through discrepancy that makes dopamine not just a signaler of satisfaction, but a true internal teacher. It compares what happened with what was expected, and silently updates the brain's predictive models about how the world works. This mechanism does not require language, does not require conscious reflection, does not require the individual to have any awareness that learning is taking place. It operates silently, constantly, revising the organism's predictions about what is worth pursuing and what is not. Each time something exceeds expectations, the signal intensifies, and the behavior that led to that outcome becomes more likely to repeat. Each time something falls short, the signal diminishes and the circuit weakens. And over time, the accumulation of these tiny, individually imperceptible adjustments profoundly and persistently shapes what a human being finds rewarding, what they seek repeatedly without noticing the pattern, what they avoid for reasons they cannot articulate, what becomes habit. The fundamental imbalance that makes this entire system work is simple in its description, but profound in its implications. The present is never completely satisfying as long as the future holds the possibility of being better. If the present were always enough, the organism would stop searching, it would stop learning, it would stop adapting. Dopamine exists in a sense because the current state is always provisional, always capable of being surpassed, always a starting point and never a final destination. It is the molecule of productive incompleteness, the messenger that tells us there is more out there than what we have already found. This mechanism of learning through prediction and error is so fundamental that the researchers who formalized it saw their work influence not only neuroscience, but the development of artificial intelligence. The reinforcement learning algorithms that taught computers to play complex strategy games and recognize patterns in enormous datasets were developed with direct inspiration from this logic that dopamine has been using for tens of millions of years to teach organisms to navigate an uncertain world. Nature solved this computational problem long before we even tried. What happens when this learning mechanism operates repeatedly, generation after generation, in a collective of organisms rather than in a single individual? When prediction error is absorbed not just by one brain but by billions of them across millennia? This question points to a scale that goes beyond the individual, beyond the family, beyond culture, and reaches something that may explain features of human experience that have not yet found satisfactory explanation in any other conceptual framework. What happens when the reward-based learning mechanism operates without interruption, every day, over an entire lifetime, when each repeated choice strengthens a circuit, and each strengthened circuit slightly tilts the next choices, which in turn strengthen new circuits, which tilt other future choices, in a cycle that consolidates over years with a persistence that no conscious decision can easily reverse. The result is something we call habit, but the word is too simple for the phenomenon it describes, so simple that it obscures more than it reveals. A habit is not an automated action in the mechanical and passive sense that expression suggests. It is a dopaminergic circuit consolidated through sufficient repetition. It is the tracing of a trail that the brain has learned to follow with less effort each time it walks it, because each journey left a signal that it was worth it, that it was a known and rewarding route, that there was no need to deliberate about it again. The first time someone incorporates a new regular practice into their life, whether morning exercise or a moment of reading before bed, the immediate result generates a response that the brain registers with some intensity. The second time, the elements preceding that practice, the hour, the light in a particular room, the constellation of sensations that compose that specific context, already begin to awaken part of the anticipation that previously only appeared after the practice had begun. By the 10th time, the context itself functions as an automatic trigger. By the 100th, the absence of the practice produces a sense of incompleteness, that is not merely psychological in the vague sense we use that word, but neurochemical, an internal state of imbalance that the organism seeks to correct. Habits are, in essence, crystallized predictions. The brain has learned that a particular sequence of context plus action plus result works in a way worth repeating, and has begun executing that sequence with the minimum conscious deliberation necessary, freeing cognitive resources for other tasks. This is extraordinarily useful from the standpoint of cognitive efficiency, but it also means that much of what we do throughout a day happens without our having truly decided to do it in that moment. They are dopaminergic circuits running in the background silently, while our conscious attention is occupied with something entirely different. This same logic of reward-based learning, when observed not in a single individual over a lifetime but in an entire community across generations, begins to explain cultural patterns that had resisted satisfactory explanation through other means. Why do certain societies historically tend to value exploration and novelty, while others consistently gravitate towards stability and continuity? Why in some groups is tolerance for risk systematically higher, expressed in entrepreneurship, in voluntary migration, in early adoption of new technologies? Why in other groups do caution and preservation of what exists manifest as core values passed down through generations? Part of the answer may lie at a level beyond socially transmitted culture: genetic variation in dopamine receptors. There is a variant of a gene that encodes one type of dopamine receptor, identified in the scientific literature with a technical nomenclature that is associated with greater sensitivity to novelty, a more pronounced appetite for intense and unprecedented stimuli, and increased tolerance for situations of uncertainty where the outcome has not yet been determined. Populations whose ancestors travelled vast geographic distances in migrations spanning millennia, crossing radically different ecosystems and facing completely unknown environments, show slightly higher frequencies of this variant than populations that remained in relatively stable territories for comparable periods. This is not determinism. It is not destiny carved in stone and unchangeable. It is a slight biological inclination, inscribed in the collective history of each human group as the accumulated result of selections made by environments that no longer exist, but that shaped the average dopaminergic profile of each population in ways we still carry. More important than the variant itself is what it reveals. Dopamine is not merely an individual phenomenon confined to the interior of a single brain and a single life. It is, in some broader sense, collective. Its variations have shaped entire cultures across generations, because the behaviors it encourages, what it seeks, what it risks, what it explores, determine what a society values, what it creates, what it passes on to subsequent generations, and what it abandons as insufficiently rewarding. This helps explain why human exploration has always existed, why it seems to be a tendency that resurfaces even when conditions are adverse, why no known species has traversed so many different ecosystems, adapted to so many extreme climates, invented so many radically different ways of organizing collective life. The human dopaminergic system has a special sensitivity to novelty, a peak of activation in the face of the unknown that is not found with the same intensity in other primates. Every new horizon that opened generated a pulse of dopamine in the organism of whoever faced it. Every successful discovery reinforced the search circuit, and over millennia, this cycle built not only populations spread across every continent, but languages with grammars completely different from one another, architectures of knowledge that organized reality according to distinct principles, belief systems that answered the same fundamental questions with radically different responses, art forms that cross centuries without losing the power to move whoever encounters them. The curiosity that leads a human being to ask how the sky works, to investigate the interior of a rock, to want to understand the behavior of a tide or the pattern of a fog is dopaminergic in its deepest nature. The satisfaction that comes from learning something genuinely new, something that slightly rearranges how you see a part of the world, passes through the same reward circuits as the satisfaction of completing a complex task. What differs is duration and depth. More abstract intellectual rewards tend to produce more moderate but more sustained activations over time, less of the sharp peak, and more of the steady current of engagement that scholars of the flow state have identified as characteristic of the most intrinsically motivating activities. When you look at the great leaps of human history through this lens, the invention of writing that preserved knowledge beyond the capacity of a single individual memory, the development of the scientific method that made collective learning systematic and cumulative, the construction of the first cities that enabled specialization and exchange at a previously impossible scale, it is possible to see in each of these leaps the structure of dopaminergic prediction error, operating not in a single brain but in a collective. A community tries something that had never been tried before. If the result exceeds what was predicted, the circuit is reinforced in many individuals simultaneously. The practice spreads. Other communities adopt it, and what was exceptional and improbable releases the search systems once again to orient toward what still lies beyond. But there is a temporal distribution of this drive that deserves attention before we move forward. The intensity of dopaminergic activity is not uniform within a single individual throughout the day, nor throughout life, nor across different contexts within the same situation. It follows the circadian rhythm, the internal cycle of approximately 24 hours that regulates sleep, wakefulness, body temperature, and dozens of other physiological parameters with a precision that clocks were invented to imitate but never fully achieved. In the morning, when the prefrontal cortex begins to emerge from the silence of sleep and the dopaminergic system aligns with the start of the day, the general tendency is toward greater willingness for initiative, for tasks requiring planning and sustained concentration, for active seeking rather than passive response. At night, when the organism begins its preparation for rest and body temperature starts to drop slightly, this same system gradually yields space to other processes, and the inclination naturally shifts toward more passive and receptive activities. The distribution is not identical for all individuals. There are genuine differences, partly genetic, that cause some individuals to reach their peak dopaminergic activation and clarity of thought in the early hours of the day, while others find that same quality later, sometimes with a lag of several hours relative to the statistical norm. This variation is not a cultural preference, not a matter of discipline or willpower, not a character flaw that education should correct. It is an expression of human functional diversity that, throughout evolution, likely ensured that human groups were never entirely unprotected during any period of the 24-hour cycle, because there were always members of the group in a state of sufficient alertness to detect what others, in their peak drowsiness, would not be able to see. All of this composes a picture that goes well beyond the individual and their conscious will. Dopamine does not operate only within a single brain, at a single synapse, in a single moment. It manifests in cultural patterns that span centuries, in historical tendencies that shape the course of civilizations, in biological rhythms that regulate when each person is more or less inclined to seek what they do not yet have. It is simultaneously the most intimate of phenomena, because it happens within every synapse of every person in every moment of every day, and the most vast, because it expresses itself in the accumulated course of human behavior across millennia. But this immense and intricate pattern would be much simpler to understand and much easier to keep within healthy limits if there were not an element that amplifies everything with an effectiveness the original biology had not anticipated, an ingredient that intensifies the anticipation signal, that prolongs the search cycles beyond any natural resting point, that drives the system into territories for which it was never calibrated. We will not name it precisely yet, but its presence can be felt in every moment the system goes beyond what any of our ancestors could have experienced. In every moment the search does not find what would satisfy it and turns back on itself as the only response. The ingredient that amplifies everything is the environment built by human beings themselves. Not just any environment, not simply the city or technology in a generic sense, but the specific set of interactive digital platforms, connected devices, and content and information delivery systems that have become an integral part of daily life in recent decades at a speed the dopaminergic system has not had evolutionary time to adapt to. To understand precisely why this environment amplifies the system in a way that other environments, even the most stimulating ones that existed before, never achieved so effectively and persistently, one must understand a specific characteristic of the dopaminergic system that spent decades being studied in behavioral psychology laboratories before anyone recognized its implications for the digital world. This characteristic is called intermittent reinforcement, and its discovery was, in the history of psychology, one of the most unsettling because of the simplicity of the mechanism and the breadth of its consequences. Intermittent reinforcement occurs when a reward does not arrive every time an organism performs a certain action, but instead at variable and unpredictable intervals, sometimes on the second attempt, sometimes on the 30th, sometimes after a long sequence of unsuccessful attempts followed by an unexpected delivery. An organism that learns to associate an action with a reward that arrives variably and unpredictably develops a persistence in that behavior that is vastly greater than the persistence developed by an organism that receives a guaranteed and predictable reward with every action. Behavior sustained by intermittent reinforcement is the most resistant to extinction that exists, the hardest to unlearn even when conditions change, the closest to what common sense calls compulsion. The dopaminergic system does not respond equally to certainty and possibility. It responds more intensely, more persistently, and more lastingly to unpredictable possibility than to predictable certainty. It is uncertainty, not guarantee, that keeps the anticipation circuits in their most activated state, and the architects of the most widely used digital platforms in the world, with direct access to behavioral data from billions of users, and with economic incentives precisely aligned to maximizing engagement time, discovered this and implemented it with a sophistication that goes far beyond the accidental. Think about what happens when you check your phone notifications. Most of the time, there is something trivial, an app update, a commercial promotion, a group message about something that has nothing to do with you. But every now and then, there is a message that matters, a comment that pleases unexpectedly, a piece of information that surprises you and that you will want to share. This variability is not an unintended consequence of platform design. It is, in many cases, a deliberate design choice grounded precisely in this principle. The unpredictability of the reward keeps the dopaminergic system in a state of constant anticipation, far more effectively than guaranteed predictability ever would. The notification bar is an intermittent reinforcement machine that fits in your pocket. Every time you scroll down, what will appear is unknown. It could be something completely irrelevant. It could be exactly what will capture your attention for 20 minutes. That maybe is enough for the circuits to activate before the content arrives, creating a state of seeking that precedes, and often exceeds in intensity, the response to whatever content actually appears. But there is a second mechanism that the digital environment exploits with equal or greater effectiveness, and that has even more profound long-term functional consequences. Researchers studying the neurobiology of desire call incentive sensitization, the process by which the brain, repeatedly exposed to stimuli that intensely activate the dopaminergic system, begins to want something more intensely, even as it progressively likes it less than it did during the first exposures. With excessive repetition of certain stimuli that activate the search system, the circuits signaling wanting become more active and more sensitive, responding with greater intensity to the triggers they have learned to associate with a particular behavior. But the circuits that generate the subjective experience of liking, of real satisfaction in the moment something happens, respond progressively more weakly to the same stimulus. Tolerance sets in on the hedonic response while sensitivity to desire remains high or even increases. The result is a behavioral pattern that anyone recognizes when they see it, and that most people recognize when they look honestly at themselves at some point. The search that intensifies while satisfaction diminishes. The person keeps opening the social media app not because it measurably satisfies them, but because the search system is more activated than ever, scanning possibilities without being able to rest, without finding the point of satiety that would naturally end the behaviour. They keep looking for something the system promises but rarely delivers, with the intensity it delivered the first few times, and the intensity it delivered those first times will never return because the receptors were downregulated precisely in response to those initial intense exposures. This sensitization explains a phenomenon that confuses people because it seems irrational. Why does someone continue a behavior that clearly does not satisfy them, that sometimes makes them feel worse than before, but which they simply cannot stop? The behavior does not continue because it is pleasurable. It continues because the search system has been sensitized enough that contextual triggers, the device on the table, the notification on the screen, the habit of a specific hour, activate a dopaminergic anticipation response that overrides conscious judgment about whether it will actually satisfy. There is yet another dimension that most people genuinely do not know about, because it falls outside the repertoire of images we have about what dopamine is and where it operates. Dopamine is not only in the brain. There is a second complete nervous system inside the gastrointestinal tract, a network of approximately 100 million neurons extending along the entire digestive system from esophagus to rectum. This system, called the enteric nervous system, produces dopamine independently and responds to it in ways that are still only partially understood, maintaining constant bidirectional communication with the central nervous system through the vagus nerve and other chemical communication channels. This means that what we call a gut feeling, that diffuse but insistent intuition we feel in our stomach before making an important decision, the intestinal discomfort that accompanies situations of intense stress, the loss of appetite that appears in moments of anxious anticipation or acute sadness, are not poetic metaphors for something happening exclusively in the head. They are physical, measurable manifestations of a continuous conversation between two nervous systems that share the same chemical messengers and that influence each other in ways that go far beyond what we can yet describe with precision. The dopamine circulating in the gut influences mood state in the brain. Mood state influences gut function. And emerging research suggests that the specific composition of bacteria inhabiting the digestive system can influence the production and modulation of these substances in ways that may one day explain why what we eat affects our motivation and well-being in ways that go far beyond simple caloric intake. How does all of this manifest concretely and perceptibly in the subjective experience of daily life, in things you already recognize but perhaps have never connected to the system we just explored? Dopamine appears as the peak of energy and clarity that surges when you start a project that genuinely interests you, before you have produced any concrete and visible result. It appears as the almost physical resistance to stopping a task when it is nearly complete, even though you are clearly tired, because the proximity of completion intensifies the anticipation of finishing in a way that overrides the fatigue signal. It appears in the peculiar and slightly irrational satisfaction of crossing an item off a to-do list, not for the task itself you just completed, but for the internal record that something has been moved from the pending category to the done category, a micro-resolution that the system celebrates with disproportionately intense approval. It manifests in the disturbed quality of sleep for someone who spent the day in excessive high-intensity stimulation. The hyperactivated search system does not wind down easily, just because the body has been placed in bed, and the mind keeps scanning possibilities and building scenarios even when the body should have already entered deep rest. It appears in the curious vividness of the first days of a trip to a completely unknown place, when everything is new and the dopaminergic system is in high responsiveness to every novel detail, and in the flattening that sometimes accompanies the return to familiar routine, as if the internal volume had been turned down several notches and the texture of everyday things had temporarily lost its ability to capture attention. It appears in the inner voice that says one more, and then I will stop, and repeats this warning multiple times at short intervals without irony, without noticing it has already been uttered several times before in that same moment, not as moral weakness, not as character failure, not as something that should be different if the person simply disciplined themselves more, as the search system doing exactly what it was trained to do over millions of years, look for the next possibility while the previous one has not yet finished dissipating. Keep the search active because stopping completely would be, from an evolutionary standpoint, a greater risk than anything excessive searching could cost. And it appears in more subtle ways that we rarely associate with dopamine because they lack the intensity the molecule's name suggests. In the genuine difficulty of sitting in silence for more than a few minutes without reaching for something that offers a pulse of novelty or information, in the disproportionate discomfort that arises when your phone runs out of battery during a moment of public waiting that would otherwise be simply peaceful, in the specific and hard-to-name feelings some people describe when finishing a long and completely absorbing book, a kind of small and precise grief for something that was organizing their attention in a way the now empty space does not know how to fill. All of this seems balanced in everyday functioning. It seems that the system, even when operating above what would be optimal, finds a new level of functioning and carries on, adapted to the circumstances of the environment it inhabits. For a long time, this impression of balance holds convincingly, but it is an equilibrium that harbours a fundamental fragility that only becomes visible when the system is pushed beyond a point that the original biology had not precisely anticipated, because that point had never existed in any natural environment throughout all of evolutionary history. The balance that sustains this system is real, to the extent that it can maintain functional coherence within a wide range of conditions, but it is precarious in the sense that there are specific conditions combining stimulus intensity with frequency, and with the absence of sufficient recovery periods, that push this system beyond the threshold biology anticipated. And when that threshold is crossed sufficiently and persistently enough, what emerges is no longer a quantitative variation of what was happening before, not simply more of the same thing, it is a qualitative change, a rupture, a different way of operating that sustains itself even when the conditions that produced it are no longer present. The first of these extreme conditions is prolonged and intensive exposure to substances that directly invade the dopaminergic system, bypassing the natural regulatory mechanisms that evolution built over millions of years to ensure the system never operated for long beyond its optimal functional range. Certain psychoactive substances do not simply accelerate dopamine production or release a little more than normal as a reward for a learned behavior. Some physically block the transporters responsible for dopamine reuptake after each synaptic transmission, preventing the molecule from being removed from the synaptic gap within the normal time frame for which the system was calibrated. Others force the massive and simultaneous release of dopamine from multiple neurons at once, completely independent of any signal the system would normally require to justify such a release. The result in both cases is a flooding of the synapse with quantities of free dopamine that exceed by orders of magnitude any level the system would naturally produce, even during moments of greatest spontaneous activation triggered by natural rewards, including the most intense ones. The brain detects this excess with a speed that reflects the precise sensitivity of its monitoring systems and responds the only way it knows to protect itself against prolonged overstimulation. It reduces the number of dopamine receptors available on the membrane of receiving neurons. Fewer receptors means that the same level of dopamine produces a smaller functional response because there are fewer docking points available for the molecule. The system is trying to rebalance itself, trying to compensate for the external excess by reducing its own sensitivity to the signal. But in doing so, in reducing the number of receptors as a protective strategy, it also reduces its responsiveness to all other dopaminergic stimuli, including those that normally produce genuine satisfaction without any artificial intervention. A conversation with someone important, a pleasant meal, a moment of recognition for work well done, an afternoon of sunshine. The threshold of response rises. What was once enough to generate a perceptible response no longer is. Only the substance, with its ability to flood the synapse at levels no natural stimulus can replicate, can overcome this new elevated threshold. Here is the point where wanting definitively separates from liking in a way that is no longer a theoretical nuance, but a reality lived with disconcerting clarity. The system seeks something with an intensity that grows with each cycle, because the search circuits have been sensitized to the extreme and respond to contextual triggers with an urgency that overrides any conscious intention of moderation. But the real satisfaction, that sense of wholeness and genuine pleasure the substance produced during the first exposures, when receptors were still at normal numbers, has been progressively silenced by the reduction in sensitivity. The system desperately seeks something it can no longer find with the original intensity, even when it obtains exactly what it was looking for, because the tool with which it processed the arrival of reward has been degraded as a direct consequence of having received too much for too long. This is the central mechanism of addiction, and understanding it precisely transforms completely how one can think about it. It is not a matter of poor choice by a morally weak person. It is not a lack of willpower in the sense that word usually carries when used imprecisely. It is a learning system that learned in the most efficient way it knows, and what it learned was that this behavior, this substance, this specific pattern of action is associated with the possibility of reward at an intensity that no other learning can surpass, because no other stimulus generated a dopaminergic signal remotely comparable. The pattern was inscribed in the circuits with a force that everyday learning patterns rarely reach, and the attempt to undo it is not simply a matter of deciding not to do something. One has decided not to do anymore. Extreme intensification of the system can also occur without substances, and the behavioral forms are in a way harder to recognize precisely because they do not carry the stigma of substances, and because the environments that sustain them are ubiquitous and socially accepted. The reward structure of gambling illustrates this with a clarity that behavioral neuroscience research confirms regularly. The architecture of these environments, whether in a physical betting house or in a betting app on a portable device, has been refined over decades to maximize activation of the dopaminergic anticipation system. The intervals between attempts are calibrated to keep the system activated without allowing the saturation process to complete. The sounds accompanying the moments of outcome are designed to amplify the emotional response during moments of occasional gain and to minimize the emotional impact of the much more frequent moments of loss. The unpredictability of outcomes itself is the central mechanism. It is this, not the frequency of wins, that keeps the dopaminergic system in a state of persistent anticipation. What the system learns is that the act of betting is strongly associated with the possibility of reward, and that possibility is enough to keep the search active regardless of the outcome it systematically produces. While you rest here, now, somewhere in the world there is an environment built precisely for this, refined over decades with this specific intention, and someone who cannot leave that environment despite genuinely wanting to. Not out of stubbornness, not out of remaining pleasure, because of dopamine, because of a system that learned to associate that gesture with that possibility at an intensity that overrides any rational argument about probabilities and consequences, that overrides the conscious will to stop, that reactivates the search cycle before any conscious deliberation has had the chance to interfere. There is another extreme of the dopaminergic system that reveals its fundamental necessity for something so basic that we rarely think of it as dependent on a specific molecule. Movement. In the nigrostriatal pathway, the progressive deterioration of neurons that produce dopamine in the substantia nigra does not happen dramatically and immediately. It is a process that develops over decades, slow and silent, before becoming clinically visible in the form of symptoms that can be detected and assessed. The system has a remarkable capacity to absorb and disguise partial losses. Surviving neurons increase their individual production, circuits reorganize their routes to compensate for what has been lost, and the organism maintains an appearance of normal functioning that hides what is happening inside. The loss of 1/3 of dopaminergic neurons in the substantia nigra may produce no noticeable symptoms. The loss of 2/3 begins to reveal what was being hidden. Beyond a certain threshold, compensation fails, and the body publicly reveals what it had lost much earlier, privately. At the opposite extreme from deficit, an excess of dopaminergic activity in certain specific pathways, especially the mesolimbic pathway, is associated with phenomena that have, at first glance, no obvious relationship with motivation or reward: psychotic states. Under conditions of dopaminergic hyperactivation in this pathway, the prediction-based learning system begins operating outside its normal parameters, finding correlation patterns where no causal relationships exist, creating associations between events that occurred close in time but have no connection to each other, attributing meaning to coincidences with a certainty the system would normally reserve only for well-established and repeatedly confirmed patterns. The brain is doing what it always does, registering co-occurrences and building predictive models of the world, but with the dopaminergic background signal so amplified that spurious patterns and real patterns become indistinguishable to the system that should differentiate them. The therapeutic interventions that attempt to address these extreme states, both in cases of excess and cases of deficit, reveal with uncomfortable precision how narrow the range of balance is within which the system functions optimally. Reducing excessive dopaminergic signaling in one pathway to treat psychotic symptoms may inadvertently reduce the necessary signaling in another pathway, compromising motivation or movement fluidity. Increasing levels in one circuit to treat motor rigidity may destabilize another. The system does not have a single lever. It has multiple interconnected pathways, multiple receptor types with different sensitivities, multiple regulatory points that interact in ways that make every intervention an exercise in delicate balance among multiple variables. In certain forms of deep depression, what is observed is not the acute and dramatic sadness that the word depression often evokes. It is frequently a kind of absence, an inability to feel pleasure or satisfaction in activities that once generated these responses naturally and consistently. It is not that the activities became actively unpleasant, it is that they stopped generating any measurable response. The reward system has lost its basic responsiveness. The inner voice that said "this is worth it, try again, this will be good" has gone inaudible, and the space where it was has become a silence of a quality different from any peace. All these extreme phenomena have something in common that only becomes fully visible when you look at them together. None of them happens in isolation within the organism. The dopaminergic system does not operate in a sealed independent box. It communicates with the immune system, which influences and is influenced by its activation state. It communicates with the endocrine system, especially with the stress response axis. It communicates with sleep and wakefulness rhythms, which in turn regulate when and how dopamine is produced and how its receptors are expressed. It communicates with metabolism and nutritional signaling pathways. Extreme conditions are invariably accompanied by alterations in multiple systems simultaneously, and trying to understand them by looking only at dopamine is like trying to understand a region's climate by looking only at air temperature. Dopamine does not live in a closed universe of chemical signaling isolated from the rest of the organism. It maintains continuous and bidirectional exchanges with other systems that regulate life, and these exchanges reveal that understanding human motivation in its totality requires looking far beyond dopaminergic neurons themselves, beyond reward circuits, beyond even the brain as an isolated organ. Sleep is the most intimate and most frequently underestimated partner of this system. During nighttime rest, especially in the deep sleep phases characterized by slow waves of electrical activity in the cortex, the brain performs consolidation and reorganization tasks that depend directly on the state of the dopaminergic system. It reinforces the learnings acquired during the day that were marked as relevant by the reward system, strengthens the circuits associated with behaviors that produce genuine reward, and prunes connections that were not sufficiently activated to justify the energy cost of maintaining them. The night is when the reward system does its internal accounting, revisits the day, decides what goes into permanent storage and what goes into forgetting. It is an active process, not a pause in activity, and it is during this process that much of what we experience during the day consolidates into something that goes beyond explicit memory and penetrates into inclinations, preferences, automatisms that guide the next day's behavior without us noticing their origin. When sleep is chronically insufficient or chronically fragmented by awakenings that interrupt deep phases before they complete, this consolidation fails in ways that only become visible over time, because each individual night seems manageable and only the accumulation reveals the deficit. The brain arrives at the next day with less calibrated circuits, with altered sensitivity to what is worth seeking and what is not. The person feels less rewarded by the usual things that normally produce satisfaction, and more drawn to high-intensity immediate stimuli that might compensate for the system's lack of responsiveness. Highly palatable food, high-frequency digital stimuli, quick reward activities, patience for delayed reward tasks, for efforts whose results only appear after weeks or months, decreases measurably. Impulsivity in decisions increases, and the organism enters a cycle in which sleep deprivation deteriorates precisely the system that should help regulate the behavior that in turn leads to more sleep deprivation. Nutrition is another point of direct contact between the external world and the dopaminergic system, more intimate than most narratives about motivation and health tend to acknowledge. What enters the organism influences the dopaminergic system through at least 3 distinct pathways that overlap and influence each other. Through the first pathway, dopamine synthesis depends on tyrosine availability, and tyrosine availability depends directly on what was consumed in the previous hours. Different dietary patterns measurably alter the availability of dopamine precursors in the brain throughout the day. Through the second pathway, the enteric nervous system we mentioned earlier processes nutritional signals from meals and sends information to the central nervous system that influences mood state and motivation in ways that have not yet been fully mapped. Through the third pathway, the gut microbiota, the collection of trillions of microorganisms inhabiting the human intestine that is different for each person according to their diet, antibiotic history, environment and genetics, produces neuroactive substances and influences inflammatory processes that have documented consequences for central nervous system function. Chronic stress introduces a layer of complexity that alters the dopaminergic system in ways that are initially adaptive but that over time become themselves a source of imbalance. Under acute short-lived pressure, in the face of a challenge that has a deadline and a possible solution, the organism can benefit from a temporary potentiation of the dopaminergic response that creates that sharpened focus, that clarity of purpose, that sensation of being completely present in a single problem that people sometimes describe as one of the most satisfying experiences they know. But under chronic, persistent pressure, without a clear resolution timeline and without sufficient recovery periods, the effect progressively reverses. Prolonged exposure to cortisol and other stress hormones begins to damage dopaminergic neurons in the prefrontal cortex, compromising the pathway that allows planning, delaying rewards, and resisting immediate impulses. The system yields to short-term pursuits with increasing frequency. Not because the person decided they want this, but because the neurological substrate that sustained long-term decisions is under enough pressure to operate with reduced efficiency. When you expand the timescales even further and observe what happens to the dopaminergic system, not over a day or a year, but over an entire lifetime, an arc emerges that has its own coherence, its own beauty, and that only becomes legible when you have enough perspective to see the beginning and the end. In early childhood, reward circuits respond with a vividness and a promiscuity that reflect the state of maximum learning. Everything is potentially interesting. Everything could be rewarding. The system has not yet built the filters that accumulated experience will progressively create. The unrestricted curiosity of a small child before any object, any situation, any phenomenon, is not naivety to be replaced by judgment. It is a learning system running at full capacity without the cost of over-specialization, cataloguing the world with the help of dopamine, finding patterns in everything, building the predictive models about how things work that will guide behavior throughout the entire life that follows. In adolescence, the asymmetry emerges that has made this period so studied by developmental neuroscience in recent decades. The reward and search circuits running through the mesolimbic pathway mature before the prefrontal cortex, which only reaches full functional development sometime during the third decade of life. The result is a period in which the search system, desire, attraction to novelty, and risk tolerance operate with high intensity and responsiveness, while the system that evaluates future consequences modulates impulsivity and allows delaying rewards in the name of long-term goals is still under construction. This asymmetry is not an evolutionary design flaw that should have been corrected. It is what allows adolescence to fulfill its specific function in the arc of human development, the period of genuine experimentation, of mistakes with consequences still limited by the protection of family and social context, of self-discovery that would not be possible with the caution characteristic of maturity. In mature adulthood, as the prefrontal cortex reaches its complete form and function, and circuits stabilize into more selective patterns, more integrated with accumulated experience, the tendency is toward dopamine that fires less frequently in response to random novelty, and with more intensity, more duration, and more meaning in response to things that have personal value built over years. The reward of the expert who solves a complex problem that is only a problem for someone with the depth necessary to recognize it as such. The satisfaction of someone who has cultivated a skill for decades and exercises it, with the fluidity of someone who no longer needs to think about the process to execute it with precision, the depth of pleasure that only exists when there is context and accumulated history behind the present experience. As the decades advance, the density of dopaminergic neurons naturally decreases as part of the general process of cellular aging, and this reduction is perceptible as a decrease in the intensity of dopaminergic responses to intense stimuli. But what longitudinal studies on subjective well-being in older populations reveal is that people who age with what they describe as quality of life and satisfaction tend to show a redirection of the reward system that is not simply compensation for decreased intensity. They are less drawn to indiscriminate novelty and more oriented toward experiences that carry relational meaning, toward human connections with accumulated history, toward the repetition of practices that generate consistent satisfaction because they have been deepened enough to reveal layers that superficial exposure cannot reach. What once required intensity and novelty to produce a response comes to be found in deepened regularity. What once required surprise comes to be found in the more precise recognition of what was always present but had not yet been fully seen. The limits of what science can assert about dopamine are honestly acknowledged by the most rigorous researchers in the field. We do not yet know with the precision we would like how early life experiences durably shape the architecture of dopaminergic circuits, and which of those shapings can be altered by later experience. We cannot predict reliably, for a specific individual, what combination of interventions will produce what measurable changes in the reward system, and on what timeline. We do not know how the high-intensity, high-frequency stimulation environment that current generations inhabit from before they learn to speak will shape these systems over the decades still to come, because the longitudinal data needed to answer that question do not yet exist. What science does know, with the clarity that comes from convergent evidence across multiple methodologies over many decades, is that the dopaminergic system is extraordinarily plastic throughout life. It changes, it learns, it can be redirected by experience, by practice, by context. Not instantly, not without effort, not in a way that replaces already consolidated inclinations with the ease we would like, but in a way that is real and that measurement instruments can document. And this plasticity, this capacity to be taught even when already established, is the most hopeful foundation of all contemporary neuroscience for anyone who wants to understand not just what their brain does, but what it can do when exposed to what is worth learning. Behind all this complexity, All these circuits and pathways and extreme conditions and connections with other systems and arcs across a lifetime, there is something surprisingly simple that seems to unify everything, something that explains why this system exists the way it does, why it operates according to these rules and not others, why it is so ancient and so persistent and so effective. You may already feel its presence, like the thread that runs through the entire labyrinth without needing to touch the walls. The thread that runs through this entire labyrinth is not merely chemical, not merely functional, not merely evolutionary, though it is all of these things at once. It is something biology expresses in molecular language, but that points beyond it, towards something all technical descriptions touch but none can fully capture. This thread is movement. Not the physical movement of muscles and joints, though it encompasses that too, but movement in its broadest and most fundamental sense, the inclination of the living organism toward what it does not yet have, toward what could be, toward the possible. Dopamine is the molecular language of movement. It is the mechanism by which life, in all its forms, orients itself toward the future. Every living organism we know, from the simplest to the most complex, from the smallest to the largest, needs something to move it toward resources and away from threats. A bacterium detects chemical gradients in its environment and moves toward higher concentrations of nutrients without anything we could call intention or desire. An insect detects the presence of food and directs its behavior to obtain it with a precision that goes far beyond simple reflex. A primate detects the possibility of reward and organizes its behavior in complex ways around that possibility, learning, remembering, planning. A human being detects the possibility of meaning, which is the most abstract form of reward that exists, and reorganizes years of their life, sometimes decades, around this pursuit that has no identifiable physical object and no guarantee of arrival. At each point on this scale of increasing complexity, there are systems fulfilling an equivalent function, making movement toward what is useful more likely than movement toward what is neutral or harmful, making the search rewarding in itself so the organism continues before the outcome is guaranteed, making the learning about what is worth pursuing something that persists over time and can be transmitted to future behavior. Dopamine is the evolutionarily sophisticated version of this system, older than mammals, older than vertebrates, older than much of what we consider typically human. It is the link between the perception that something could be good and the act of moving toward it, between the world that exists and the world that could exist if the search was successful. And here is the deepest level, the layer that none of the earlier parts of tonight touched directly, because it needed everything that came before to be fully legible. Dopamine is not simply a pleasure system, not simply a motivation system, not simply a behavioral learning system, though it is each of these things. It is, at the most fundamental level of its function, a system for learning about value. It teaches the brain what has value, what deserves continued effort, what justifies persistence in the face of cost. And it does this not by external decree, not by rigid programming that does not change, but through the accumulated experience of attempts and errors, of surprises and confirmations, of disappointments and discoveries, over an entire life that unfolds one synapse at a time. This has a consequence that transforms the question of free will in a way that most philosophical discussions on the topic do not reach because they lack neurobiology as a starting point. When people discover that their behaviors are influenced by circuits operating below consciousness that do not ask permission before generating the impulse to seek, the initial reaction is often a disturbance that seems logical, as if discovering that dopamine influences choices were equivalent to discovering that choices do not exist, that what we call decision is merely the narrative we tell after the circuit has already decided. But this conclusion, however much it seems to follow from the premise, does not hold up when you carefully examine what the system actually does. Because dopamine does not prescribe what should be valued. It learns what has been valued. It listens. And what it listens to, what enters as information to be learned, is determined by what the person exposes themselves to as experience over time, what they choose to repeat, what they choose to abandon, what they choose to cultivate even when it is difficult. When someone decides, with effort and with enough repetition for the effort to leave a mark, to expose themselves to certain experiences and not others, to cultivate certain habits and abandon others, to devote time and attention to certain activities and not others, they are doing something that goes beyond simple, conscious choice. They are teaching the dopaminergic system a new vocabulary of value. They are rewriting, slowly and without guarantees of speed but with guarantees of direction, the relative weights the system assigns to what it encounters. The system learns, the circuits reconfigure. What was costly and against the current becomes progressively more fluid. What was indifferent begins to produce satisfaction. This process is what researchers call motivational neuroplasticity, and it has been documented with instruments of increasing precision in studies following people who adopt regular practices of meditation, sustained physical exercise, learning skills that require years to mature, habitual contact with natural environments. Meditation has drawn the attention of neuroscientists for a specific reason that goes beyond its general effects on stress. It appears to decouple the search system from its dependence on specific external objects. Long-term practitioners show, in neuroimaging studies, a greater capacity to find satisfaction in attention itself, in the quality of presence in the moment that is happening, without the need for that moment to contain something specifically new or specifically pleasurable to activate the dopaminergic response. The system does not disappear, is not suppressed, but it learns a new repertoire of triggers, a repertoire that does not depend on novelty, on external intensity, on unpredictable variability. Reward no longer requires an external object to justify it. This process resonates with something that contemplative traditions from different parts of the world articulated in completely different languages and images long before any neurological measurement instrument existed. Most of the great traditions of human wisdom arrived, through radically different paths, at a structurally similar intuition. The suffering that accompanies desire does not come from desire itself, which is an expression of vital movement, but from attachment to a specific outcome, from the inability to find satisfaction in the very process of searching regardless of where it leads, from the confusion between the value of arrival and the value of the journey. Dopamine, which has never heard of any of these traditions and which has existed far longer than any of them, confirms this intuition from an angle none of these traditions could have anticipated. It fires in anticipation, not in arrival. It is in the process, not in the outcome. A system that evolved to keep organisms moving toward what they have not yet reached discovered, without any intention or planning. That movement has value in itself, that the search is part of the reward as much as the finding. This opens a perspective on satisfaction and happiness that contemporary neuroscience is only beginning to articulate with the precision the subject deserves. Deep and sustained satisfaction, the kind people describe when they look back at periods of their life with the feeling that it was worth it, is not the state in which dopamine is constantly elevated above baseline. That state, when artificially maintained long enough, leads to system exhaustion and progressive insensitivity. What studies on subjective well-being and meaning across an entire lifetime consistently associate with lives people retrospectively describe as satisfying as an oscillation, moments of intense search and anticipation, followed by arrival and integration, followed by genuine rest, followed by new movements toward what is not yet here. The rhythm, not the constant peak. The healthy variation, not the ascending linearity that modernity often proposes as an ideal. There is a form of dopamine that does not depend on speed, does not depend on novelty, does not depend on increasing intensity to remain present. It is quieter, more constant, more like a tide than an isolated wave. It is the dopamine of practice, of craft, of commitment to something over enough time for its deepest levels to begin appearing. When you do the same thing with genuine attention, day after day, and notice that something difficult begins to feel natural, that something requiring conscious effort begins to happen with a fluidity that surprises whoever observes from outside, the dopaminergic system responds to this perceptible progress with a satisfaction different in quality from the satisfaction of the acute peak, not in bursts, but in rhythm, not an explosion, but in sustenance. While you rest now, exactly here, the dopaminergic system is in its nighttime cycle. The circuits that were activated during today's hours are being silently revisited, strengthened where learning was marked as relevant, integrated into what was already built before tonight. What you encountered here tonight, not as isolated information going into a drawer to be forgotten, but as a piece fitting into something larger you already knew before you could name it, is being stitched into the fabric of what you are. Tomorrow, something may seem slightly different from how it seemed before. A connection may emerge where before there were only two separate fragments you did not know belonged to each other. The sentences can grow shorter now. The search rests. The system breathes. You are made of circuits that learn to value what you repeated with attention throughout your life. And you can change what those circuits value, slowly, with gentleness, with persistence that does not need to be heroic to be real. You are safe. What moves you, this silent inclination toward the possible, is part of the same inclination that moves the cosmos toward its next form. You are part of this. You always have been. While you rest, somewhere in the world a neuron fires, a signal crosses a synapse, and something that did not exist a moment ago comes into being. This happens inside you too, even now. Even in silence, everything is in order. The universe continues its silent dance and we rest in its embrace. Thank you for walking with me tonight. Sleep well.